All right, let's get started. Hello, welcome to new CS491 High Performance Concurrent Computing. My name is Jacob Eriksson. The idea of this class is to learn how to write fast programs. So we're not going to worry too much about complexity of an algorithm. The program is already provided. Maybe someone else wrote it and they're asking, why is it so slow? This is really low complexity algorithm. Why is it running so slow? And that's we're going to learn the tools that we need to use to diagnose why. We're going to learn to know the parts of the computer system that we need to understand in order to try to fix the problem. And finally, we'll learn some techniques for fixing the problem and making your machine run as fast as it can. And so overall, the class will be extremely hands-on. Some of you, I recognize, you know the kind of class that I teach. We'll have lots of homework assignments, probably 6 to 8 assignments. There will be a lot of performance debugging, right? Trying to figure out what's wrong with this program. Sometimes there's something actually wrong with it that I've introduced, and sometimes there'll be a normal program that millions of people use, and we'll try to find ways to make it better. And so the general idea is you're going to get a lot of practice with getting making programs go faster. So, okay, I have prepared some course materials. Now, this is a brand new course. Hopefully I get to teach it many times, but it's heavily under development, so bear with me. But at least we do have a syllabus. So maybe we'll go through that first. The syllabus is available at this, or the class website overall is CS491 hpcc.class.uic.edu. And that's where we'll be posting homework assignments, the class schedule. In fact, we can go back and take a look at it. All right, so it looks something like this. The layout, it's not my fault. And then you'll find the syllabus, you'll find the various assignments that are just being populated, you'll find the class schedule. Over time, I'm recording this lecture, I'll record all lectures. Over time, this sort of schedule that's here now will be replaced by individual lectures, perhaps with some lecture notes associated, and certainly with a link to the lecture recording. This page. Very important is the Piazza link over here. That takes us to the discussion forum, which we'll no doubt use quite a bit. So far, it's unclear if we'll have a formal TA, but certainly some of my PhD students will be helping out in the class. They're not here today. All right, so let's take a look at the syllabus. Right, so I guess in order to write a fast concurrent program, concurrent meaning parallel, running in multiple threads, I think we first need to know how to write a fast single-threaded program. So we'll look a little bit at that in the beginning of the class, the first couple of weeks. There's a lot more to concurrency than just p-threads parallel programming. In particular, we'll look at the other kinds of concurrency in your normal computer system. You'll see a lot of I/O concurrency. Whenever you try to request something from disk, let's say you're reading something from a disk, there's concurrency. Whenever you just execute a few instructions, it looks like, in assembly, it looks like, oh, we have these instructions back to back, but in fact, they're usually running in parallel to some extent. A normal CPU will be executing up to, I believe, at the moment, I think we're up to 168 instructions that are running all in parallel, except it looks to the assembly programmer, the C programmer, like they're running in sequence. So if all you want is correctness, actually that doesn't really matter. If you just want the program to execute the instructions that you give it, Intel pretty much provides that, and AMD. But if you wanted to go fast, you sometimes have to be aware of this concurrency in order to kind of help the machine run as much in parallel as possible. So we'll look at that. So we'll talk about a variety of profiling and debugging tools that we need in order to see what's wrong with the program. I didn't put it in here, but we're going to have to learn how to sort of sort of make a back of the napkin calculation. How fast should this thing run? Right? So we have this for loop, and we're doing something for each iteration. Well, roughly how long should it take? If it takes a minute, is that right or wrong, or about where you would expect? Maybe it should take only a microsecond and it takes a minute. Then it's good to be able to catch that sort of thing. Now, a microsecond versus a millisecond, a factor 1,000, maybe we'll get there. Right? But a factor 1 billion or 100 billion, that probably we should catch. Okay, so we'll look at, right, so I guess that's the first thing. We want to measure how long did it take to run the program. There's a handy command line tool called time, and it just tells you it took this long. All right, so now we look at that and we have some idea how long it should have taken. We see, okay, probably something's wrong. Then we can start doing some profiling and debugging. So we'll look at that a little bit. In an SMP system, that's where you have multiple cores running in parallel. And almost every laptop in the room, or even cell phone in the room, is an SMP system these days. There you have now concurrent threads of execution that are actually running together. If you have only a single core, it appears like they're running together, but there's only actually one running at any given time, and they switch sort of seamlessly between each other. That is a very different performance situation than an SMP system where they're all running at the same time and potentially competing for resources. That could be I/O, that could be usually the bandwidth, the bottlenecks will be in memory accesses. We'll see that for a bit. I guess there's also synchronization. I'm sure you're aware by now that you need to synchronize. If you have multi-threaded programs, you need to synchronize access to any shared data structures. Otherwise, you're going to get bugs in your program, race conditions. But that synchronization can also be incredibly slow. Right, so we'll get a decent idea of how the cache coherence systems in a normal SMP machine works. That is, how is it that you can have this cache that keeps copies of the data in memory, and yet you can oftentimes expect a reasonable result. If two threads are accessing the same part of memory, they have their own copies of that memory. How does that even work? Both in terms of correctness, which there isn't that much of, which we have to sort of provide at the system, the system layer, operating systems and runtime and libraries, such. But also in terms of how this impacts performance. Most of you have probably done a bit of pthreads programming. Who's done pthreads programming? Who hasn't? Who isn't just answering? Just isn't answering. Right. Okay. All right, so pthreads programming, almost everyone. If you haven't, it's not a big deal. We'll probably do a brief review of that. It's kind of clunky. You say, go run this thread, and then now you have go run this function. You have one thread running that function, another thread running this function. To coordinate the two, it works great if you have like a specific thing you want that one to do, and another specific thing you want this thread to do. But if you want them both to work on the same problem, then it gets kind of awkward. So OpenMP is an alternative. I can't remember what MP stands for, multiprocessing maybe. That basically hides a lot of the extra work. It makes it easier to do what's called data parallel programming. Don't trick yourself into believing that OpenMP uses the processor in a different way. The only kind of thread that exists is a a hardware thread provided by the CPU, or a kernel thread provided by the kernel, or a user thread provided by a user threading library. This OpenMP relies on normal threads. It just kind of makes the operation a little more convenient. So we'll use that quite a bit, I think, to kind of set up some examples and try to build some fast programs. Then we'll take a look at, we'll do a review of this explicit multi-thread programming, also called task parallel programming. That's your normal p-threads. And synchronization primitives like barriers and such. That should be pretty quick. But then we'll see how the synchronization operations are implemented. So in a normal systems programming class, you would use your pthread lock and be happy. But if we're trying to run this fast, pthread lock isn't always the right solution. So now we want to understand what are the performance implications of a spin lock or a pthread lock or a Q lock. There's lots of different choices. And why do we get those performance implications? Now we're starting to get into the nitty-gritty of the system. At the beginning of the class, it's pretty high level, and then we start getting lower and lower in the hierarchy, I suppose. So we'll look at various alternative lock designs, memory allocation methods. Let's see, that's not actually in here. On a typical larger machine these days, memory isn't actually equally fast all over the place. Some addresses will be slower than other addresses depending on which core you're running on. So we'll look a little bit at that. I hope we'll get to this. This is sort of my favorite topic at the moment. Delegation is an alternative to synchronized access to shared data structures. So you don't do locking, you do something different. Maybe that'll be toward the end of class. And there are a couple of other things that I hope we'll get into. It depends a little bit on how things go with the rest of the class, how much you're prepared, how much I get prepared. But we may do some GPU programming, probably with CUDA. I've ordered some GPUs, maybe we'll do something with that. A GPU is a graphics processing unit, like what you use for gaming, let's say. They were built for that, but these days you can use them for general purpose programming as well. They're kind of weird. I can have, say, 8,000 hardware threads running at the same time, but all of those threads are really weak. They have not a lot of memory, they don't go all that fast, and they all have to do the same thing all together at the same time, and you have to do a lot of setup to use them. So we'll try to get a grasp on when one should be trying to use GPUs and when it's better to just run single-threaded on a single core and forget about the rest. It's not always clear that you want to use concurrent computing. Sometimes you just want to optimize the hell out of that one thread, and it's much better. So sort of trying to get a grasp on that would be useful. And then there's SIMD programming, which is somewhat related. This is also called vectored programming, vector instructions in typical CPUs, where you say, oh, here's 8 integers, and here's another 8 integers. Now multiply all of them by all of those. So you can get kind of one single instruction, multiple data. And so that will be extremely efficient for some types of computing, and other times completely useless. So it all depends on what we're doing. So we'll try to do something in that direction as well. This is not in any particular order. I probably should reorder it. Memory consistency models, that has to do with what you can expect from the cache hierarchy or the memory hierarchy. If one thread writes to an address, when can another thread actually expect to see the result? Not just in terms of time, but in terms of sort of a causal sequence of events. There's lots of different memory consistency models proposed and provided by different hardware and languages. Okay, before I continue, I want to get a little bit of background on you folks. Who has taken CS361 here at UIC? All right. And that would be with Chris Kanish. No, with Taylor. All right. Who's taken operating systems? 461, 385. All right. I think I saw only faces that I recognize. No, did you say you've taken OS as well?
Yeah.
Not with me, right?
No.
Yeah. This was with John Bell then, perhaps?
Schatz?
Sol Schatz, holy shit. Okay, yeah. Yeah, that's a while back. That probably won't give you much background for this class, but that's okay. Sol was a very conceptual guy. Okay, let's see. I had some other questions here. Oh yeah, who is comfortable with assembly programming? Okay, a little bit. C programming. Okay, or at least you think so. We're not going to be doing a lot of assembly programming in this class. Yes, we'll be doing C programming for sure. We will probably be looking quite a bit at assembly. The compiler will generate some assembly for us, and maybe we'll tweak it a little bit. Maybe we'll add some inline assembly here and there to see what happens, right? Little things. But we're not going to be writing large assembly programs. Nobody in their right mind does that. But we will be doing mostly C programming. I think I mentioned somewhere that we might be doing Rust. Who's done any Rust programming? 2. Rust is a real pain in the ass. What's really nice about Rust is that if you get the program to compile, generally speaking, it's not going to crash. The problem is it's really hard to get it to compile. The compiler is very, very strict about what you're allowed to do. It's a very fast language. It's a systems programming language, which means it compiles to assembly. It doesn't have a garbage collector. Pretty much the result looks like a C program, except with some extra fluffy subroutines. But basically, it's straight up assembly. But there is an extremely strict type system that makes it difficult to write programs in it, and makes it even more difficult to write buggy programs, which is great. Maybe we'll get there, but I fear we won't. Probably we have enough to deal with C. At some point, I hope that people can move away from C overall. C is like a very thin shim layer on top of assembly. It pretty much compiles straight to assembly, and, well, at least without running the optimizer, the compiler optimizer, you can pretty much expect what you're going to see in the assembly code with a bit of experience. Whereas, let's see. Right, and the compiler doesn't do much else. It has some fake type checking, but there isn't really much going on. Whereas in other higher level programming languages, you can get very good correctness checks, but you have no idea what's going on. There's no way to tell what instructions are going to run, and so it's going to be very hard to write a program that performs as you expect, because you don't know what it's going to do. It'll just you just have to hope for the best. And Rust is one example where you kind of get both. You know what it's going to produce. Code is going to produce. You can write an operating system in Rust, which you can't in almost any other language except C. Yeah, either we're all going to have to get used to the compiler being what it is, or someone will come up with a sort of a nicer language that does the same thing. We'll see. All right. How many PhD students in here? 1, 2, 3. All right, pretty good. Master students? Half the class, and the rest are undergrads. Cool. That's a typical mix in a 400 level. What else did I have? Oh yeah. Did anyone? I guess everyone has taken a computer architecture class. Who did not? All right. So you haven't seen assembly in the past, or? Okay. So you've taken. Okay. So I would usually an assembly class. That'll be a computer architecture class. Right? Okay, that's fine. So we'll be doing everything in x86 assembly here, just because we're going to be running on real machines. Some of my research lab machines will be used for the class, and you'll do some things on your laptop. But basically everything's x86. Okay, let's continue down the syllabus a little bit. Oh yeah, right, this is also kind of important. We're not going to talk about anything distributed in this class, other than distributed within the machine. You could sometimes the boundary isn't quite clear. In a multi-socket motherboard, it's not quite clear if this is a distributed system or a centralized system. But if you have shared memory, normal shared memory, then we call that not distributed. So we won't be talking about cloud computing, MapReduce sort of concurrent programming. MPI is what you run in supercomputers. MPI is just a way of sending messages between computers and between threads. None of that is covered here. Everything will be on a single machine, not leaving the sort of network interface, I suppose. And we're probably not going to worry about complexity of algorithms at all. Now, the complexity, generally speaking, is the high order bit. There's no point in optimizing your program for performance unless you've fixed your complexity issues first. Once you have that, generally speaking, if someone who only knows complexity has written the program, it's still going to have lots of room for improvement. We could be talking about thousands of times. But 1,000 times isn't much compared to, say, exponential complexity. Right? Who cares about factor 1,000 constant? Okay, so the class will be meeting here unless we manage to get a better room. It'd be nice to have windows, maybe. But at least we have a projector. I have office hours today, right after class, and then Wednesdays between 1 and 2 p.m. in my office. That's on the 13th floor of SEO. The elevator only goes to 12, and then you take the stairs up to my office. We probably will have a TA, Ben Bainan, but it's a little unclear. Depends on how many of you I manage to scare away in the coming 2 weeks. And he'll have some office hours. Or if not, there will be various PhD students kind of pitching in and having office hours now and then, helping out with the homeworks. We'll see how that works out. Okay, the goals we talked about already. Prerequisites. If you're an undergrad, you really must have taken 361. It's great if you've taken OS, but it's not really necessary. It helps a lot with kind of reasoning about performance to know what the OS is doing too, because every time you make a system call, now suddenly the OS is doing something. So if you call malloc, right? Does that produce a system call? Is malloc a system call? We have one no. Any yeses? Okay. Well, malloc is not strictly a system call. Will it produce any system calls? Mm-hmm. Right. So can we have some names? Yeah. Oh, I think, is it BRK or SBRK? Same difference. All right, so that's one. Raise the size of the heap. Right. So knowing that might happen is very good. There's another one called mmap that it might also use, and kind of having a grasp on the difference between raising the brake and an mmap call is something that you would get out of an OS class, possibly out of 361, or at least some aspects of it. We'll see how much you need, that sort of thing. Okay, if you're a grad student, you really should understand computer systems. Like, you should be relatively comfortable with GDB, with make files, with disassembling some objects. Like, what does it mean to link a few object files into an executable? I'll try to review some of those things along the way, but the only way I can do that is if you let me know. Right? I'll be making some assumptions, some sort of arbitrary assumptions about what you know, and I'll go fast on the screen, and I'll show things, and if you don't know what's going on, just tell me, and then we'll stop, and we'll do that instead. I don't use slides, and so it doesn't matter to me. We'll just, as long as we get something good out of the class, that'll be fine. And we'll be doing some concurrent computing along the way, I'm sure. I forgot to bring, there is no textbook. I'm working on a sort of a PDF of class notes and something like that. We'll use that, and we'll use a whole bunch of links to various websites, and we're certainly going to use man pages and probably some Stack Overflow and this and that. There's one really excellent book that doesn't really cover, it's called Distance Performance, but it doesn't really cover like the optimization side of things as much. Okay, yeah, that's the one. But if you're interested in measuring system performance, there's an excellent book that I can recommend if you want to kind of build your library. We will also certainly be using this website quite a bit. Brendan Gregg is whatever performance engineer at Netflix, and he does a lot of this open source tools for diagnosing performance in systems. So some very useful tools that we'll be using throughout the course of the semester, I think. You could also just take a look at this website, brendangregg.com, if you want to kind of review a bunch of tools and get an idea. All right, back to the syllabus. Okay, this one is never very fun to review, but the point of this class is for you to get lots of practice on your own figuring out why a program's going slow and how we can make it run faster. So the only way you can learn that is by doing it on your own. You are expected to turn in your own work, right? There's no copying of code at all. Of course, now we have the excellent resources on the internet. You'll find snippets that probably are useful. And what's the point of typing it in, right? Go ahead and copy paste it. But if you find solutions to my homework problems and you copy paste that, clearly you won't get any points. And if you, but you still won't have any academic integrity problem as long as you put a citation, right? So if you're using code from somewhere, even if it's the complete homework solution, as long as you put in a citation, you'll be okay. You get 0 points. If I'm getting copied homework solutions from somewhere else, and there's no citation, then we'll have more serious problems. And unfortunately, sometimes it's hard to tell like who wrote it. There's no proper attribution on the internet for anything. So maybe it was your solution, but you put it in your public GitHub account, and someone else found it. And so now both of you are going to get in trouble. So don't share your code on GitHub, and don't copy other people's code without citation. So the general idea is do your own work, but of course, I mean, there's excellent references online, and there's nothing wrong with copying a few lines of code here and there. That's how things work. So I'm fine with that, but you won't get much credit for what's copied. Okay, any questions on the academic integrity thing? There are no group projects, so that makes it easier. All right. The course is graded in 2 ways. There's going to be a whole bunch of assignments. That's worth half the grade. And then there will be 2 exams. The midterm is worth 20%, and the final is worth 30% of the course grade, so that adds up to 100. I don't know how many homework assignments there will be yet, so we'll just divide it out. But basically, you're going to have a hard time with the exams if you don't do the homeworks. And usually, I've noticed my exams tend to be harder than the homeworks. I mean, the homeworks are a lot of work, but you can usually kind of grind through it and figure it out. But an exam is not like that, right? So I would recommend that you put in lots of effort on the homeworks so that you have all those points and all the skills that you get from there, and then the exams will kind of follow. There's not going to be a whole lot of book reading things for the exams, right? We don't even have a textbook. Point is to make sure that you kind of remember what you did, or certainly hope that you did the work, and then if you've done the work, then you'll be able to figure out the exams as well. That's the general idea. I don't know anything about what the curves will be like. Generally speaking, in my classes, people kind of end up in different cohorts. There'll be some people who are just going crazy well, and some people who aren't doing any of the homeworks. Those are the A's and the F's. And then in between, usually it's a pretty natural distribution. I'm not going to say, oh, everyone needs to get at least 80% or you're not passing. It's not like that. I want to see serious effort, and then we'll see how the exams turn out and the homework. Sometimes the homework will be too hard, and I'll try to make up for it. So it's basically a sort of a relative thing, but it's not like there's 8 A's that will have to be distributed throughout the class. If everyone does a brilliant job, you all get A's. Right, and I will grade graduate and undergraduate students separate. Usually there's no telling who will do better. Usually PhD students will do better. But among master students and undergrads, sometimes the undergrads are the winners, sometimes master students are. It doesn't really. So it doesn't make a difference, but by the rules, they need to be graded separately. So we'll do that. Or curved separately. Right. Let's see. Oh yeah. If things are a little too easy, or if you feel that you need more challenges, feel free to talk to me about that. I'll try to find some other things that you can do. Some of these, if you've been doing a whole bunch of profiling in the past for the first couple of homeworks, maybe it'll be that easy. Maybe you need some more challenges. Feel free to dig into a lot more of what Brendan Gregg is writing about, like how things work in the Linux kernel for profiling various system calls and whatnot. There's an awesome amount of information and some really cool tricks being pulled in there that we're not going to cover. So I can point out reading and such if you're interested. Questions for me? Come on, one question. Yeah.
Talking about C and Rust, what about Go?
No. Go is not bad. Go is a good language. I prefer systems languages. And so Go is somewhere in between, where you don't really know what's going to happen, but it probably will go fast. I don't have much experience with Go, but my understanding is that it is very good for sort of networked services. Still applications, but on providing network services. It's evolved at least into a sort of special purpose language for that sort of thing. So if you're writing a web server, cool, right? My specialty has become a little lower than that, and lower layer than that, and it's better that I teach the things I know. Yeah.
Will we go over how code should be written if it's optimized to run on a GPU versus just normal threaded code on like a computer that has multi-threading?
Yeah. So we'll try to get a good grasp on the differences between CPU multi-threading and GPUs, and also other kinds of concurrency. Right? There's the data parallel versus the task parallel. There's the SIMD concurrency. There's this implicit instruction level parallelism. You can write code to target all these different kinds of concurrency. Hopefully we'll have at least a decent idea of what's what toward the end of the class. All right. So The homework isn't up yet. The first homework isn't up yet. It'll be due on next Thursday. I want to make sure the first homework is due before the end of the 2-week period, right? So that people can make informed decisions. It'll be about profiling a program. There's an existing large-ish program that I've introduced a whole bunch of weird bugs into, performance bugs. So it runs really slow, and it'll be your job to figure out why. There's a whole bunch of different bugs that are well hidden in the program. So in order to do that, you can't read this program and figure out why it's slow. I mean, I'm good at hiding these things. There's maybe 1 or 2 that will stick out if you were to read the entire program, which is long and complicated. The only way to really figure it out is to use profiling tools. So we need to be able to measure an existing program that you didn't write, right? And much of the semester will be doing that sort of thing. Maybe also improving existing programs. So I thought we'd just kind of take a brief look into some of those tools that we can use. And we'll certainly spend a lot more time at this, on this later on. And I'll also do a little bit of concurrent stuff now, but which we won't touch for quite a while. But yeah, we got to do some sort of intro demonstrations, so why not? Okay, so let's see. Should I use Emacs now? Maybe. All right, yeah, I have an example program in mind. I wrote a Python program. It's been a while. So this is the general idea. I have a range 1 to 1 billion, or is it 0 to 1 billion? Doesn't really matter because I'm computing the sum of them. So I want to see what is the sum of all those numbers. And so how long is this going to take? Naturally, if you're very clever, you could figure out the sum without doing the for loop. Right? But let's not do that. Let's just run it instead. So let's see, I'm going to write this to, oh, I think we have it. Oh. All right, I want to tell you a little bit about my setup too, because you're going to need the same one, essentially. I have a Mac. We can't run this on the Mac. We need Linux tools. You're going to need a Linux virtual machine that you can do things on, compile and such. It doesn't matter, it doesn't need to be fast. You probably have received an email from Phil Beltran or from VMware something, or something about VMware. I recommend that you get a VMware hypervisor like this one. This is what it looks like on the Mac. There's something very similar on Windows. You create a small virtual machine, give it a few gigs of disk and some memory. Performance isn't important for this. Okay, so the way I run this is I just start the virtual machine as a server. It just has an SSH server running on it, and then I SSH to it. I call it Linux here. I call the machine Linux. Who has taken 450? Okay, some of you. All right. You don't have to give it a name, but in here on a Linux or any Unix machine, if you put something in host, that's a nice shortcut. Doesn't matter. Use whatever SSH you want. If you want to go this route, and you should only do that if you actually have a Unix machine already that you're running it on. If you have a Windows machine, the correct solution is install do a virtual machine with Ubuntu desktop, so that you get the whole Linux experience with a Linux command line and a Linux editor and Linux everything. Windows tools are going to get in your way. Yeah.
What's the Windows subsystem for Linux? You have Ubuntu, Debian, and all that stuff.
Sorry, what's that?
The Windows subsystem? I guess you can like boot bash into Windows and.
Yeah.
that would
Yeah,
work.
it's basically Ubuntu terminal on Windows.
That sounds like a terrible idea. If it's a virtual machine provided by Windows, so that it runs a Linux kernel in a virtual machine, totally fine. No need to use VMware. If you have sort of a shell that pretends that it's Unix, but it's not, it's going to give you. It won't even work for the first homework for sure, and after that, it's over. But this is really good. So the way it looks for me, so I just have this. I don't have this graphical thing, but it is a very good idea to also use the graphical Ubuntu if you want. There's nothing wrong with that at all. I just happen to prefer the Mac desktop because that's where I have everything else for my lectures. Okay, so I SSH into it by saying SSH Linux, or the IP address of the virtual machine, and now I can just use it like any normal server. And then I like to use my Emacs on my Mac. So now the files are hiding inside a virtual machine. So in order to get access to those, I use something called SSHFS. Let's see, it's very convenient. Actually, let me make another one. So if you've taken operating systems with me, you may have somewhat of an idea of how mount works because you implemented one. If you haven't, it doesn't really matter. Here it goes, SSHFS. My Linux machine, the colon just says my home folder. Stick that in Linux 2, the local folder, and now in Linux 2, which I just created, is the stuff from my home folder in the virtual machine. Really good tool. And this will work with any SSH server, of course, but for now, we're just using our virtual machine. Later on, I have some very big servers that are across Halstead in our data center. And the plan is that you guys will all be able to run experiments on those with, say, 64, at least 32 cores, maybe the 64-core machine, we'll see. And for that, you will certainly need to use SSH and such to move things around. So please get used to that. And please use the command line stuff. Like, don't use PuTTY or that sort of thing. Get used to using the command line because you get so much more power when you learn to put all these different commands together on the command line. You can't put the graphical stuff together. So it's just sort of good practice. Okay, so I have that set up. I'm just gonna, what was it, Linux 2. So now it's not in there anymore. It's just hiding in the virtual machine. But I also have my Linux folder, that's why. Okay, so I think I saved that already in some.py. So let's see how long that takes to run. So I SSH'd in there, and where was it? All right, any guesses?
20 seconds.
Okay, 20 seconds. 2 seconds. Those are both very good guesses. They're, within a couple of orders of magnitude, which is fine. Let's just run it and see, because it takes a little while. It's really, really hard to tell with Python, because we don't really know what it does. We know we want it to add a number to another number, and we know the CPU has a facility that can do that in one cycle, right? In fact, a half a cycle or a quarter cycle, because you can run 4 adds at the same time on a normal Intel machine. Of course, you couldn't really do 4 of these at the same time because they look kind of sequential. But anyway, we ought to be able to do billions of them per second. And it doesn't look like Python's doing that. It's doing something else. Who knows what it's doing? But I think it's almost done. I tried it before. I think it was 46 seconds. So 20 seconds was a fantastic guess. 2 seconds actually isn't such a bad guess either. I thought we'll try it in C instead. Actually, let's try one more thing. Let's see. There's a couple of simple tools that we should definitely get used to. We already ran time here, right? So this is great. Real says, how long did it actually take? This kind of the wall clock. Has nothing to do with what you were doing. It's just like the time between starting it and ending it. User says, how much of the time, of that time, that's always going to be smaller than the real time. Actually, no, I take that back. If you run it on a single core, it'll always be smaller. But if you run it on 100 cores, it might be 100 times bigger. It counts the number of CPU seconds spent on the CPU by this process. It says user because you're in user mode. So the program is executing like the stuff that you see here. Well, it's not doing anything near what you see there, but somehow it at least intended to do that. And then there's, so it's working on the behalf of this program, right? That much of the time. And then it says, how much time was spent in the kernel? So in this case, the kernel doesn't really get involved. You're adding numbers. We don't need help with that. But if you're doing other things, if you're allocating a lot of memory, if you are reading from disk, if you're trying to access shared data structures, perhaps, you might end up spending a lot of time in the kernel. So kernel work happens when you make a system call and when you have a page fault. Well, maybe we'll talk about page faults later on. But basically, it's tracking work that was done by the kernel on behalf of this program. So, sometimes you'll be switching between programs. The kernel says, okay, now I'm running this, and it switches to another one, and it keeps track of like, okay, but I spent this much work on that, on behalf of that program, and then maybe some of it is on behalf of no one, and that doesn't really get tracked. Okay, so this is the sort of the most primitive possible way of measuring performance of the program, but it already tells you quite a bit. While we're on this, let's try another one. It's a cool program called cat. I don't know why it's called cat, actually. Has nothing to do with animals. But if I say, like, hello, then it prints out the whatever I said. And so you can give it a, you probably have done before, where you say cat and then a file, and it takes that as input. But the default behavior is it reads from standard in and writes it to standard out. That's all cat does. So how long did it take to run cat? Well, it hasn't finished yet. But so I hit Control D to say there's no more input. I give an end of file on the input. And so here it took 35 seconds to finish cat. Of course, it didn't actually spend much time on the CPU. It wasn't like spinning, waiting for this. And it wasn't spending any time in the kernel either.
Is that rounded up?
What was happening then? Is it rounded up? Yeah, I would think so. That's still a millisecond. It didn't spend that much time in the kernel, but yeah. So, where was it? If it wasn't running user stuff, it wasn't running for the system, and it still took 35 seconds to finish, what was it doing?
Waiting at input?
Yeah, and what does a program do when it's waiting for input? What's that?
Just
If it was idle spinning, it would be either user or in system. It was sleeping. All right. It was sitting in a queue somewhere in the kernel, not at all using the CPU. It's just sitting there saying, okay, whenever someone provides some input on this file descriptor, wake me up. Until then, I don't care. So it's not using any CPU. You'll find in this homework, this next homework, that we're spending quite a bit of time probably real, largely because of bugs, and quite a bit of time, real of course, quite a bit of time. Quite a bit of time user, quite a bit of time in the system, but also quite a bit of time just not doing anything. And we'll have to figure out why. Okay, so let's do a, yeah, I wanted to see how fast is this thing going to go if we write it in C. Sum.class. Yeah, I tried it in Java too. It got really confusing. Actually, why don't we do it? So here is my Java program. And if I run that, that finished in 600 milliseconds. So this could mean that Java is fast. Hard to tell. And I have no way of figuring out what Java did, unfortunately, because it compiles the bytecode. We could try to read the bytecode. It's been over 20 years since I last read bytecode. And then once you have the bytecode, then you have to run it. And that means this Java runtime is compiling it on the fly into some assembly. And it might change its mind at any moment and compile it again to something different, or just interpret it. So it's a little hard to tell what it's actually doing. It did something, and it produced the right result. I recognize that number. In 600 milliseconds. So that's good. All right. So how long should it take to do it in C then? Let's see. Sum.c. Come on. I don't know how to tell Emacs to not complete that. All right. So we'll write the sum program again. Oh, I think it needs to be a long, doesn't it? Right. Okay, what do you think? I can compile. Oh, my sum. Okay, what's going on? So sorry about all the warnings, but I don't want to type all the includes and stuff if I don't have to. All right, so same number, but it took over 2 seconds. So maybe we should just use Java instead. Huh. Okay, so what do you say? Should we try to, we don't know what Java did. Should we try to parallelize this thing? Let's do it. So I'll just, this OpenMP is awesome. I mean, it's both awesome and weird and ugly. And you have to decide. But you just go like this. Pragma omp parallel 4. That's it. All right, so now it's going to run this for loop in parallel. Oh, one more thing. Like that. Maybe I should actually get rid of the errors. Come on. What? Did it not save? There. One more thing. Oh. What's the... Oh, okay. Fine. Oh. Okay. Thank you, OpenMP. So let's see, how long did it take? Maybe it was faster at least. It's a trade-off, right? Correctness versus speed. Okay, so that didn't work as expected. What happened? go right back to the source code. It's very clear what's going on here, right? You're actually kind of losing this benefit of C already. With this pragma stuff, how the hell is that running in parallel, right? The parallel code, the only way to run parallel programs on any machine that forget the GPUs, but on any CPU sort of machine that I'm aware of, is you start a thread, meaning start running this function and then go down. It's always like that. This is just hiding it. It's doing the exact same thing. So I think this, when you say pragma omp parallel, then you have, it's automatically starting a bunch of threads. It's running these threads, and they start running a function called like omp worker or something. And then this for rewrites this for loop to create a whole bunch of little tasks, probably little functions, that they then say, oh, this worker, send a message somehow to one of these worker threads, go and do a little bit of the for loop, right? So there's all this stuff going on behind the scenes, much like high-level languages, and so we don't really know what's going on. But now that we know that's how it's implemented, maybe you have an idea of why we got the wrong sum. Cache inconsistency, yeah, something like that. There's nothing wrong with the cache hierarchy as such. The problem is maybe a little simpler than that. It's a race condition, yeah. So we have a shared variable and we didn't lock it, and so what do you expect? Basically what happens is you say plus equals I, so you read the value of the sum. That's actually, this translates to exactly the same thing as this. Right? So it reads the value of sum, and at some point later, it adds I to the sum, and then it writes it back. At that point, sum has already changed by a lot. And so you're going to overwrite and get all sorts of weird effects. Yeah.
Doesn't OpenMP like take care of locks?
Nope. OpenMP doesn't do anything. I mean, yeah, it does translate this whole loop. You know, it'd be a real pain to try to parallelize this loop this nicely with pthreads. So it does something, but it doesn't help you with correctness. But what you can do, and there's many different ways. There's locks also in OpenMP, and in fact, we could use a pthread lock in here if we wanted. That would get weird, I think. But it probably would work. But the easiest thing to go is like this pragma omp critical. And so what I will do is create a critical section. In order to, to be safe here, I think we probably should put curly braces. So it'll make a critical section of the rest of this curly brace. So now it's locking some anonymous lock, but it's going to be the same lock for all of them anyway, so we don't care. And that will be good. So now how long is it going to take? Actually, it'll produce a correct result, I think. I hope. Let me see. Oh yeah, and if you don't provide this flag, then it doesn't, all this pragma stuff doesn't do anything.
How many threads is it going to make?
That's a very good question. Let's see. Looks like 2. Lame. Okay, 2. Could be faster than running it on a single thread, right? Could be twice as fast.
Probably faster than having 10,000 threads, I would think.
Let's try it. Oh, I should compile it. So without synchronization, it took 2 seconds. Yeah, so OpenMP figures out how many threads there are available on the machine and starts a bunch of workers based on that. But it seems to be having some issues. Maybe it's because we don't have enough threads. So we'll go to one of our bigger machines. This one has 64 cores, 128 threads. So it took 35 seconds to compute, but it's the right result. So that's good. So parallelizing didn't really help, but maybe the problem is that we only had 2 cores. So what's the point? All this overhead for just 2 cores. So let's try running it on, and it's even on a virtual machine. So I'm not sure they're really properly cores. So let's try running it on 128 hardware threads. And at some point later, you should have access to that sort of experiment yourself. Compile it. All right, so now we're running probably on 128 threads. Hard to tell, right? Because I didn't tell it how many, and it'll just do whatever it thinks is right. Maybe we'll just leave that. It doesn't seem to have gone much faster. So maybe we should back up a little bit and see how fast could this go? You know, if we're, yeah.
Why was parallel execution still slower than the single-threaded?
Hard to tell so far. We haven't really got into that. But there is some sort of coordination required between these threads. Like whenever if you run it without a critical section, then in principle, they ought to be able to go faster, but they won't produce the right results. If we do have synchronization, now they have to wait for each other, like, oh, now I want to read the sum and write to it, and then you go. So in this case, in the previous case, we had 2 of them kind of fighting over it, going back and forth a lot. And now we have 128 of them fighting over it. In fact, there's no parallelization here. Everything we're doing is one critical section. And so they're all just standing in a line trying to acquire that lock. And that's all that's happening. I think maybe it gives a little flavor of sort of the dangers of parallelization. There has to be some actual parallel work. I don't know if this one's going to finish today. We'll see. So I'll just leave it there for now. But how long should it go? Let's say we just forget about this OpenMP, because that wasn't really practical at this point. If we just have a single thread, how fast should that run? It's 1 billion of them. Right. So this is going to expand to, every time around the loop, there's a comparison. And there's an increment of this loop variable. Comparison and a branch. Right, so that's 3 instructions. They're not very complicated instructions, but they do have to go in sequence because they all depend on each other here. And then there's this incrementing. So it looks like that's a load and an increment and a store. So, you know, maybe we're 10 instructions or something total for the loop body. And we want to go 1 billion times around. That's 10 billion instructions. It's, you know, figure a 2 gigahertz machine. So 10 billion instructions for 2 gigahertz. So it should take a few seconds, right? A couple seconds. So how did Java run in half a second? Let's try this. Let's go with a, yeah.
Oh, were you asking like for a guess as to why?
Yeah, why not?
Could you do less comparisons and just put more summation inside the body of the for loop?
Yep, in this case we can, because the compiler knows how many times around it needs to go. So it could, in principle, expand this loop. It's called loop unrolling. Oh yeah, I forgot to mention this in the syllabus. We'll talk a little bit about compiler optimization techniques too. What are the tricks the compiler will pull and the CPU will pull to go faster. Okay, but anyway, here we have, we know it's 1 billion operations, so in principle the compiler could expand this loop to just make 1 billion sums back to back. That doesn't sound like a good idea, but maybe you'll just do 1,000 and then go around 1 million times. That'd be pretty good. Let's just try this with with the optimizer enabled. So generally speaking, we don't, if you just compile without any flags, there won't be much optimization happening on the code. You're gonna get really dumb code. With the maximum optimization level here, there's O2 and O3. They're kind of both maximum in their own ways, but O3 is usually a good one. Let's try it. What happened? So now we ran in. This is only because the time doesn't show less than milliseconds, right? But it finished in less than a millisecond. So it looks like C is anyway faster than Java, or if that's the way to put it. But what happened? Because we're running 1 billion instructions, no, 10 billion instructions in a millisecond. So do we have like a terahertz processor here, or what's going on?
The compiler already computed the result and just assigned.
Yeah. So these are all of this can be computed in one go. Right? The compiler got very clever. Rather than unrolling the loop, it just computed what will the sum be at the end, and just put the sum in the sum, and that's it. Because all of them are constants. If we were to take an input, maybe we should try that. I haven't done that. Let's see. Of course, this is taking longer than I expected. I think the compiler got really dumb here. Somehow didn't realize that this, probably because it's a pointer, I don't know. It's decided to run A to I over and over and over here every time we're on the loop. That's why it took so long. So let's do a, come on. See what we get now. Somewhere in between. Yeah. So here, yeah, I know what happened. Okay. Let's try, just because, let's try one more. So we had it in there, the sum. Now I just stick the sum outside. See if that makes a difference. Okay, and then this, oh, volatile, sorry. And now this ought to be a lot slower. Yeah. Okay, so anyway, I think the point here is very, very small changes in the code can result in absolutely enormous differences in performance, and it's often a little hard to tell what's going on. So at least by just reading the code. So we need tools. Next class we'll talk about some of the tools. We need tools to measure directly where are we spending the time, so that we can spend our own time optimizing the lines that matter and ignore the rest. Does anyone know what happened here when I say volatile?
Volatile means that it has to keep checking the value of sum because other things can change it?
Exactly. So this sum here, well, it actually means maybe both that and one more thing. It means that, yes, it'll change at any moment, or basically, there may be other threads accessing this variable. And so it's not okay to just assume that it'll stay the same, and you also should be writing out to it as often as you can, because others are going to be looking at it. So it's not safe to keep this in a local, keep it in a register. If we write it like this, then the compiler will load the value of sum at the beginning of the for loop and keep it in there until it's done with the for loop and then write it out at the end. I think, let's see, why don't we do one of these. See if we can find it. Last minute. Ooh, look at that. That is an unrolled loop. Cool. All right. Yeah, we won't get into these details, but basically all of these instructions, they all look the same because the compiler decided, let me just do 10 at a time. Something like that. I think we'll skip the rest there. Okay, so I think at least hopefully this gives you a little flavor of what the class will be like, right? We'll be having weird programs, running tools, looking at assembly, measuring things, and trying to learn things together. All right, I will see you on Thursday, and I'll post on Piazza about the homework. It'll be ready tonight.